The interpotential interval varies from one motor unit discharge to the next due to the neuromuscular transmission. Some variability also occurs due to noise, interference, artifacts, or other phenomena such as the velocity recovery function. In general, the individual interpotential intervals appear to vary randomly about a mean value. Sometimes one observes a trend in the interpotential intervals. The mean value progressively increases, as here, or in some cases it may decrease. The neuromuscular jitter is then seen as variation in the interpotential intervals superimposed on this trend. Among other things, trends may be due to a change in the propagation velocity in the two fibers that produce a potential pair. For example, if the velocity of the second fiber decreases more than in the first, the interpotential interval will increase. Conversely, if the velocity in the first decreases more than in the second, the signals will approach each other. That is, the interpotential interval will shorten. Another cause of trends in the interpotential interval is a change in the recording needle electrode position. The actual interval may change, or the amplitude of the signals may change, which will then influence the measured interpotential interval. This is shown in these two time-locked potentials. We will trigger on the second potential. Due to the short time interval between these signals, we're using a fast sweep of 200 microseconds per division to see the waveforms clearly. During the following video, the amplitude of the potentials initially increases slightly and then decreases. Note the change in the relative positions of the peaks of the potentials as their amplitude falls. Let's review the traces from the stored signals. All 100 sweeps are shown superimposed here. Here we see 5 superimposed signals acquired at the beginning of the recording. A. Halfway through the recording, B. And at the end of the recording, C. Showing how the progressive fall in signal amplitude produced the progressive increase in interpotential interval. The MCD for this recording is 9 microseconds. The trend in interpotential interval is seen very easily in the sequential interval plot here below. Since the mean consecutive difference, the MCD, is computed using successive IPI values, the trend does not have a significant effect on the calculated MCD value. The mean sorted difference, the MSD, does not compensate for trends, and thus gives a higher jitter value. In some cases, the difference between MCD and MSD may be much higher than in this recording. Other measures of variability, such as standard deviation, also do not compensate for trends and would give high values of variability. The MCD is therefore the most robust measurement of interpotential interval variability when there's a trend in the intervals. Details about the calculation of jitter can be found on pages 52 to 54 in the single fiber EMG book.